Hi, my name is Untitled Chapter from UC Riverside. Today I'm talking about our project Frugal, how to Thrifty object detection and tracking for mobile augmented reality. So augmented reality or AR is a hot topic with the devices that are forecast to have $100 billion in the market by 2021. Also, AR is a killer app right now in the market with gaming, like Pokemon Go, or the translation application like Google Translate. So basically, in AR, virtual objects are overlaid on top of the real-world objects in order to provide information related to the physical objects. Therefore, object detection is an important task in the AR pipeline. So, because object detection can provide the object location and their classes in order for the AR to overlay related information on top of the object. So we can see on the left-hand side example here that, okay, we have object detection that can detect this printer and where it is in the frame and also the class label of the printer so that AR can render related information on top of that. And deep neural network or DNN can provide highly precise object detection, but they are energy heavy on mobile devices. We tested AR application running continuous DNN, and we start from fully charged phone from 100% battery, and within 1 hour, the battery dropped from 100 to 55. Which means that it drains 45% of battery within about 1 hour. So the design goal for this kind of object detection based AR system is this. So we need to have precise classification because we don't want to overlay information related to a cat on top of a dog. Also, we need real-time accurate tracking of multiple or potentially moving objects in order for the user to have a seamless experience of the AR. You also need effective but energy-saving techniques, such as the technique that called mobile CPU throttling, because we know that if we have heavy computation on mobile CPU continuously, could trigger CPU throttling would impact the performance of the system. You also need to take advantage of this like mobile GPU techniques to save energy or compress DNN to save energy. We also have to cope with this dynamic camera due to the handheld or wearable AR devices. So our problem statement is this. How can AR apps achieve good object detection and tracking performance and yet consume low energy? So the key idea is that, okay, if DNN is heavy, so we interleave DNN with some lightweight methods, such as object tracking or change detector. But still there are several challenges based on that idea is that how can we design these trackers or change detectors to be effective yet lightweight? And how often do we trigger these lightweight methods? We don't know now. And also how to cope with this automatic CPU throttling on the mobile devices. So we have this following contributions. We developed a framework called MARLIN to mediate between DNNs and lightweight methods. And we design a lightweight change detector to determine when to trigger DNNs. We evaluate MARLIN on Android smartphones using standard datasets and with the right experiments. So on the standard dataset, we can save up to 73% of the energy by using our system. And on the live experiment, we can save up to 81% of energy. So our system is compatible with a developer's chosen DNN. For example, one developer like YOLO, they train the model, plug into our system, it works to save energy. Another developer have mobile nets, plug into our system, save energy. Another developer like mobile GPU use it and then save energy with our system. On average, it's around 45% energy saving with MARLIN. So we'll talk a little bit about the design of MARLIN framework. So the architecture is simple. We have in MARLIN we have MARLIN Manager sitting in between the phone camera and two lightweight methods and one heavyweight method, which is DNN. So basically, MARLIN Manager intercept camera frame and forward that frame to object tracker and change detector. Receive feedback from object tracker and change detector as the track status and change status. And based on those feedbacks, it decides whether or not to send the frame to the DNN object detector. So MARLIN is thrifty. Thoroughly, forward this frame to and trigger DNN all even it needs to do that. And after that, it's simple. Just combine the result from the object tracker, combine result from the DNN object detector with the frame, and then forward to the drawer, which render the result on the phone screen. So the next part of our design is real-time object tracker. So we have quite a requirements here, right? That we need to be fast, we need to be low power. So we use we use all image features together with Lucas Cranach optical flow. This combination of the techniques that provide very good tracking outcomes that run within 10 milliseconds for a location updates on the phone, and is low power using only 200 to 300 milliwatts power. One more important aspect is how do you know that the tracker failed, and then you need to trigger DNN to recover from that failure? We need to use kind of an estimation of the tracking accuracy because we do not have the ground truth. For the live system, we don't have the ground truth to say, okay, this is exactly the accuracy that the system is giving. So we use an estimation of the normalized cost correlation, which basically measure the object feature similarity between two frames. And we use this in NCC as an estimation of the tracking accuracy. So for example, in this example on the bottom, you see that, okay, from frame 1 to frame 2, this car looks similar, and NCC is like almost 1, it's very high. Then the car drive past some kind of trees, having this occlusion, the NCC is dropped. So it depends on the MARLIN Manager to decide whether or not to trigger and to recover from this failure. Also, we need to have a lightweight change detector. This is cool because we have, again, multiple requirements. It needs to be real time, it needs to be low power, it needs to have low positive rates, and it has to ignore existing objects that are being tracked in object tracker. So existing method, you search in the literature, it would point you to background subtraction. But background subtraction is too susceptible to camera motion. When the user is moving camera, background move, you say, oh, this is the change happened, triggered in and again, but it's actually not that significant change in terms of AR, then consume energy more again. Our method is a random forest from with the input of the image feature as the color histogram. So it is fast, it works around 4 milliseconds on phone, it's low power, less than 100 milliwatts energy consumption, and it's accurate when compared to other machine learning techniques that we have in comparison. For example, it has higher precision and recall compared to support vector machine using hot features. So this is an example of how this figure on the right bottom is an example how our chain detector works. So on the left-hand side, you can see that when the chain detector receives input from receives frame and also receives information about object being tracked by the object tracker, it wipes out that object on the left-hand side. It doesn't care about that. Then, after wipe out that part, it still sees object of interest, which is cost, right? Then it say, oh, this chain status is true. Send this information to the MARLIN Manager. MARLIN Manager say, oh, okay, we need to do something, we need to trigger the image to recover, we need to track this object of interest. On the right-hand side, you see that the object tracker already tracked these two horses. You don't see it, but I can tell you they are horses. Then when the chain detector wipe out those objects, saying this detected, oh, there's no object of interest, it's already some background. Then we change status to the manager as false. We do not to say that, okay, MARLIN manager doesn't have to trigger in right now, and then save a lot of energy without losing any accuracy here. So the last component in our system is DNN object detector. Basically, it's like the DNN can provide highly precise classification and detection. It extracts image features automatically and pass these features to convolutional layers and output class level together with object locations. And we use off-the-shelf DNN such as you know, YOLO, tiny YOLO, mobileness, GPU mobileness, quantized mobileness. You can plug them in, MARLIN, and you save energy. So this is evaluation of MARLIN. The experimental setup we have is that we have Google Pixel 2 running Android 8.0 and LG G6 running Android 7. For that phone, we use for automatic throttling experiment. We have data set to train and test, so we use ImageNet video for offline experiment, and we use VOC and PenFidan pedestrian to train it for live experiment, but we need to track people for that live experiment. For training, we have training validation, we have 350 videos for that, and then use 15 to 80 audio videos for the online testing. For the baseline, you can see on the next slide, baseline means continuous execution of DNN. Just let it be, the one DNN will be triggered after the previous one finish. So this is the main question of our paper, like how much energy does MARLIN save? So we have a plot of accuracy and energy. In accuracy, we show the IOU intersect over union accuracy and the power consumption in watts. So we have, as I mentioned, we have baseline and MARLIN. Baseline meaning, for example, baseline YOLO meaning that running YOLO continuously, baseline MobileNet running continuously, or use quantization or use GPU. And MARLIN means that we use that model plug into our system, and then again test accuracy and power consumption. So the takeaway, one takeaway is that you can see here on the right hand side that quantization and GPU save energy, right? Help save energy for the AR system. But when we plug them in our MARLIN framework, it further reduces the energy consumption. And for that, I have the number, it saved 45% of power after we already after the GPU or quantization already saved for the mobile phone. And another takeaway is that you can see on the left-hand side in terms of accuracy, you can see that the tiny YOLO is the best baseline to compare with MARLIN because it provides the highest IOU accuracy. So when you compare with the best baseline, which is tiny YOLO, we can be experiment with more video on this experiment, up to 80 videos in total. You still see the same trend in which MARLIN extend battery life, say energy extend by 1.85 times with only small accuracy loss. And when you compare video by video and then have relative accuracy between tiny YOLO and MARLIN, we can see that from the CDF plot on the right hand side that for 46% of the videos, MARLIN can even improve the accuracy. And this is interesting, because MARLIN already saves energy. Sometimes it increases accuracy as well. Why? So we're going to see it in an example case study here on this slide. So this is an AR system that is tracking hamster, only hamsters. So like zoom in video, right? You zoom in the hamster and you want to have the AR tracking you. So you can see from the right-hand side plot that MARLIN can improve over time. Can improve the accuracy over time. Why the tiny YOLO gets stuck at around 50% IOU. that happening? So the baseline tiny YOLO, because it's execute VNN frequently, sometimes VNN return a bad result, return bad feature for the system to track. For example, you can see on the left-hand side that for this VNN return not only hamster but a false positive dog, and then the system track based on that result, leading to a low classification precision of 0.5. On the other hand, MARLIN at some point allow 2000 frame index. Around that point, it finds a fluid and stable input feature to object tracker and change detector. When it finds that good features, it doesn't need to trigger in and use the use object tracker to track the object without the bad result that we see from the baseline and YOLO. So for this video, MARLIN can have 55% gain in terms of the classification precision. It can save 2.5 watts of power and extend 3.5 hours of battery life. So, and the next experiment is about CPU throttling that I mentioned already. So, as you know, automatic CPU throttling can save energy. That's kind of the purpose of CPU throttling. But does MARLIN still help in that situation? So we test MARLIN with again the baseline tiny YOLO on the CPU throttle phone. Because when CPU is throttled, when you, for example, we run VNN continuously for 1 minute, 2 minutes CPU throttle, you see, oh, save battery, I'm happy. But in fact, the tracking latency increase. When tracking latency increase, you can lose the tracking accuracy. Right? And that's the impact of the CPU throttling. So MARLIN, when we use MARLIN, it reduces VNN execution, reduce the instances of the throttling, and then improve the tracking accuracy and further reduce the power consumption from already saving from the CPU throttling. We also have a live experiment. I want to thank my friends in the lab. I asked them like when they had, and then, oh, let's do it. I have one guy holding 2 phones, Google Pixel 2, one phone running tiny YOLO, the baseline, and the other phone running MARLIN, and tracking 2 or 3 people in the field of view. And those people, the AI user move, those people move, blah, blah, blah. We have the detail in the paper. But basically, from the result, we can see that the accuracy in terms of IOU doesn't lose much when we use MARLIN. It's like comparable accuracy. But in terms of power, it's significant. With MARLIN, we only use 20% of the battery that's used by tiny YOLO. And 50% in the second experiment, only 50% energy use of the energy used by the tiny YOLO. So basically, because in the second experiment, people move more and there are more people in front of the camera. So, in conclusion, energy consumption is a major concern in AR. As you see already in the beginning, that the battery percentage dropped a lot. But 45% of the battery drops after just 60 minutes of using this car. We designed MARLIN to be power thrifty, object detection and tracking for AR. That is compatible with multiple VNN models. It basically intelligently alternates between VNN and lightweight methods to achieve high accuracy while saving around 45% of the energy. Our future work includes we want to incorporate inertial odometry to further save the energy of the phone. Thank you.